The lecture on digital processing of drone images will start. Today's theme is Introduction to 3D Modeling. This lecture will cover the basics of 3D modeling, including wireframes and textures, followed by discussions on photogrammetry and drone-based POI, point of interest, photography. Furthermore, a recently popular 3D generation AI will be introduced. So, let's get started. Prologue. 3D modeling is a field of computer graphics. It involves creating three-dimensional objects, such as objects, characters, and buildings, in a virtual space within a computer. The basic models used for this include wireframe models, surface models, and so on. The inputs used to create these models include coordinate data in three-dimensional space, and numerical data representing texture, light, and other properties. Therefore, this lecture will explain the basic and important terminology you should know when learning about 3D modeling. Wireframe model and surface model. A wireframe model is a model in which an object is composed of wire-like lines. In the two models on the left, the orange parts represent edges and vertices, respectively. In the two models on the right, the orange parts represent faces, which are the areas enclosed by edges and vertices. A surface model is a model created by applying the following processes to a wireframe model: coloring and lighting of the surfaces. All four models in the figure are surface models, and the orange parts correspond to the orange parts in the models above. Texture. The original meaning of texture is to weave, or woven fabric, and from there it came to mean tactile feel, texture, feel, and the structure and material feel of an object's surface. In computer graphics, a texture refers to a two-dimensional image or pattern, applied to the surface of a 3D CG model. This expresses texture and patterns, such as tree bark, metal rust, and the texture of cloth, giving a simple model a realistic appearance and depth. Texture mapping is a technique for applying a 2D image as texture to the surface of a 3D model. This mapping includes techniques to enhance realism by expressing color, texture, and unevenness, and by considering lighting. Examples of 3D modeling. Let's take a look at some examples of 3D modeling. The image on the left is from the 3D floor plan page on Wikipedia. This is a bird's eye view of a house's floor plan, used to explain the layout to clients. By adjusting the size and placement of windows and columns, or changing the interior design, it helps identify what the client prefers. The image on the right is a 3D modeling illustration from Wikipedia. It creates a highly realistic CG image through details such as the donut's color and lighting. Since it is a CG image, it is easy to change the type of donut, lighting, and background, making it simple to identify attractive donuts that appeal to the market. Next, examples of 3D modeling. In computer graphics, it is possible to animate 3D models. By virtually simulating the movement of objects that cannot be observed in reality, we can gain a deeper understanding of their mechanisms and fundamental properties. The example on the left shows the operation of an internal combustion engine. It illustrates the movement of mechanical components such as pistons and valves, as well as the timing of fuel intake and combustion in relation to these movements. The example on the right demonstrates how the movement of heart contributes to blood flow. The URLs for both examples are posted in the description box, so please watch the videos there. Here, in both examples, the color and light reflections change in accordance with the movement, creating a high sense of realism, which allows users to become deeply immersed in the experience. This is where the strengths of 3D modeling truly shine. Methods for obtaining coordinate data for 3D models. There are two main methods for obtaining the coordinate data: vertices, edges, and faces, that make up a 3D model. Measurement and acquisition from physical space, objects. This method involves obtaining coordinate data from physical objects or terrain using methods such as photogrammetry or 3D laser scanners. Software generation. This method involves creating coordinates in a virtual space using 3D CG software. The following are some of the most common file formats for storing acquired coordinate data: point cloud data, .loss, .ply, .pts, .xi. Polygon mesh, .obj, .stl. and others. This lecture will cover measurement and acquisition from physical spaces and objects. As measurement and acquisition from physical spaces and objects, the following are commonly used methods for 3D measurement for 3D modeling. Photogrammetry, which uses photographs taken with a camera. 3D scanner, which primarily uses lasers to obtain coordinates in 3D space. Comparison of photogrammetry and 3D scanner is shown in this table. Looking at this, if you need something easy to use and accept low accuracy, photogrammetry is a good choice. If you require high accuracy, using a 3D scanner is recommended. If you want to see this table in more detail, please press the pause button to stop the video. Photogrammetry. Photogrammetry is a coined word meaning measurement using photographs. That is the combination of photo, gram, and metry. Here, the word gram refers to grammar, the technique for writing characters, and its derivatives include program, histogram, and grammar. In this lecture, photogrammetry is the science and technology of obtaining reliable 3D measurements, models, and maps from 2D photographs. Photogrammetry apps that are available commercially will be introduced. These can be broadly categorized into PC software and smartphone applications. Recently, lidar-based applications have become common, but there seem to be very few that are suitable for 360-degree measurement, including the area behind an object. Next, the 3DF Zephyr as PC software will be introduced. 3DF Zephyr. 3DF Zephyr is a commercial photogrammetry and 3D modeling software. It is a product of the Italian software company 3DFLOW, and available on Windows platform. Its features are: it uses proprietary libraries. Its free version allows importing up to 50 photos, as of October 2025. It can automatically sample videos. It is widely used academically, cited in over 100 papers, according to Google Scholar. This diagram outlines the process by which 3DF Zephyr takes materials as input and outputs a 3D model. Input to 3DF Zephyr is material such as photos or videos. This is split into multiple photos. The spatial arrangement of each photo is estimated. Dense point clouds are generated. This is used to generate wireframes. Next, meshes are generated. These are then output as a 3D model. Let's look at an example of 3D modeling. The subject is a penguin doll. Here, I'll hold a camera and film a video while circling the penguin. That's the video below. It's currently playing at 4x speed. Also, the original video has various objects in the background, so black masking to make modeling easier is applied. The result of 3D modeling is displayed on the PC screen. What you see now is a 3D model of a penguin doll. This model is rendered with light projected onto it. You can move and rotate the viewpoint using the mouse. To see the wireframe, turn off rendering. To do this, perform the following steps. Now, a wireframe composed of triangular meshes is displayed. Next, let's remove the color from the point cloud. To do this, perform the following steps. The color is gone, and a white wireframe is displayed. "3D modeling using video footage of a drone performing a point of interest orbit will be performed. In this video, a person is standing in a field, and the person is the subject. Due to the approximately 46-second recording time, the sampling frequency of 3DF Zephyr was set to 50 frames divided by 46 seconds nearly equals 1.1 fps. The results are shown below. The way you view the 3D model can be changed using the mouse. Looking at this, you can see a general depiction of the field and people, but you can see that the detail, especially the accuracy of the human modeling, is low. This is likely because, compared to the penguin example, the camera range is wider, and despite this, only 50 photos could be used, preventing a thorough analysis of the object's details. Recently, 3D generative AI has become quite well known. For example, Meshi AI and Hitam 3D are famous ones. This explanation will clarify how these differ from photogrammetry. Photogrammetry is a technique that involves taking dozens or hundreds of photographs while circling an object, and then combining them to create a 3D model. It accurately creates a 3D model of the object using numerous photographs. On the other hand, 3D generative AI is a technique that generates a 3D model from one or a few photographs of an object. Because AI infers the shape of the backside and other parts that are not visible in the photographs, the resulting model may differ from the actual shape of an object. The displayed 3D model was estimated by Meshi AI using only one photograph of a penguin doll. You can see that the beak is a little long. Next is the back view of this model. Looking at this, you can see that the tail is longer than it actually is. In other words, 3D generative AI has the advantage of being able to easily estimate the whole from one or a few photographs. However, you shouldn't expect to get a highly precise model. Thank you for watching. This lecture ends here. Please watch for the next lecture. The URL for the next lectures are listed in the description box. If you like this lecture, please subscribe to my channel.